Hello everyone, and welcome to the first video on relationships between two quantities. In this video I will give you an overview of the topic, and in the next few videos I will discuss each of the subtopics in more detail. To begin, let's take a look at what it is that we expect that you will be able to do after you watch these videos. Here is a formula. PV is equal to nRT. This formula applies to any system that consists of a gas inside a container. For example, this could be helium in a balloon. It could be oxygen in a steel tank. It could be a mix of fuel and air in a cylinder with a piston on top. It could even be the air in your lungs. P refers to the pressure of the gas. V is the volume that it occupies. N is the amount of gas, how much of it you have, how many molecules. T is the temperature. And the fact that it's capital T tells me that the unit is in kelvins. R is a constant. It has a fixed value. The numerical value in SI is 8.314. Now when I take a look at this formula, there is a lot that I can tell. For example, I can tell that if N and T remain constant, so we don't let any gas enter the system or leave the system, and we also keep the temperature constant by, let's say, putting it in in water at constant temperature so that we can cool it or heat it. It could be this kind of a system. If it's sealed and the mixture of fuel and air cannot escape, then N is constant. And we can also keep the temperature constant by, again, putting that in water and keeping the water at a constant temperature. Now, in such a system, if I double the pressure by pushing on the piston so that pressure doubles, I get half the volume. Twice the pressure, half the volume. I can tell that if pressure goes up 3 times, volume goes down to 1/3 of its value. And it also works the other way. If pressure goes down to half its value, volume doubles. So increasing pressure decreases volume. Well, that much of it is obvious. But what's not quite obvious is that if you double the pressure, volume goes down to exactly half its value. My apologies. My phone happens to profs too. And now other things that I can tell about this system, about this formula. Let's say that we want to see what happens if pressure if temperature changes. So now our focus is on these two quantities, pressure and temperature. We now expect that volume and amount will remain constant. So for example, this could be this scenario with oxygen in a steel tank. In a steel tank, the volume is pretty difficult to change. And if it's sealed, then amount is also constant. Now if I heat that system so that the temperature doubles in kelvins, then pressure will double. If I cool the system so that the temperature goes down to 1/3 of its value, then pressure goes down to 1/3 of its value. I can tell why they wrote the formula in this particular way and not some other. There are so many different ways to write this formula. As an example, we could move T diagonally down, turn multiplication by T into division. We can take V and move it diagonally down, turn multiplication by v into division by v. And then we would get P over T is equal to NR over V. And of all the different ways of writing it down, they chose this particular one. The reason? Because it reminds me that changes in the product PV, which correspond to mechanical work, such as pushing down on the piston, appears as change in the internal energy of the system, which is heat. And therefore, the work that I do by pushing down on the piston appears as heat within the system. Here is another formula. Temperature in degrees Fahrenheit is equal to 32 plus 9/5 times temperature in degrees Celsius. I can look at this formula and say that water freezes at 32 degrees Fahrenheit. I can tell that every time the temperature goes up by 5 degrees Celsius, it goes up by 9 degrees Fahrenheit. I can tell that if the temperature goes down by 18 degrees Fahrenheit, then it has gone down by 10 degrees Celsius. Here is a third formula. D is equal to Vt. D is distance that you cover. V is the speed of travel, which is assumed to be constant, and T is travel time. Now, if V is constant, my speed doesn't change. Then I can tell that driving twice longer, I cover twice as much distance. If I drive 1.5 times longer, I cover 1.5 times as much distance. Now, let's say that D is fixed. This time we are talking about, let's say, the distance between two cities. And we allow V and T to change. So now we are focusing on these two quantities, speed and time. And I can tell that if I drive twice faster, I will get to my destination in half as much time. If I drive 1.5 times faster, then I also know that the time that it takes will go up by about 2/3. Now, under perfect conditions, of course, these are exact. So these are the formulas and what we expect that you will be able to do after you watch the videos. Now, a couple of questions. Number one, why is it that we focus always on two quantities? And the reason for that is because it's easier to establish a relationship between two quantities when those are the only things that are allowed to change. To explain how that is the case, imagine the situation where we have an agent that can affect the state of a target. Let's say the target is the amount of money that a kid has, and the only way for that kid to get money is from a parent who is the agent. Now we know that if the amount of money that the kid has goes up, we know where it comes from the parent. Now let's imagine a situation in which there are two parents, and both of them may contribute to the allowance that the kid gets. Now, if the kid's money goes up by a certain amount, I will not be able to tell who did it, who gave the money to the kid. Was it parent number 1? Was it parent number 2? It could be that some of the money came from parent number 1 and some came from parent number 2. And if there are more agents, that makes the situation even more complex. You can imagine in the problem PV equals nRT, if we allow temperature, amount, and volume, all three of them to change, then pressure changes. But we won't know whether pressure changed because temperature changed, or did it change because amount changed, or was it volume? Maybe it was a bit of each. Maybe the change in temperature had some effect on the pressure, and the change in amount had some effect on the pressure. But I cannot establish any kind of definitive relationships. Now, if we allow only T to change. So we keep amount and volume constant. Again, you can think of the situation that we had with the steel tank. If it's sealed, amount is constant. And because it's made of steel, the volume is very, very difficult to change. And if temperature is the only thing that's allowed to change, then I know that if pressure changes, that's because temperature changed. And I can also investigate how the change in temperature affects the pressure. For example, if I double the temperature, will pressure double? Will it get divided by 2? If temperature goes up by 10, will pressure go up by 10? Maybe it goes down by 10. I can set up experiments and figure out how changes in temperature affect the value of pressure. Now, of all the different kinds of relationships that we have, we need to come up with some kind of classification so that we know at any point in time whereabouts we are and where we are headed. Now, the question of how do we classify the different relationships runs along the same theme that all of the series in this channel is about, that mathematical tools evolved as a result of our problem-solving needs, and therefore we can always teach and learn mathematics by focusing on the simplest kinds of relationships and problems, and then moving on to more and more complex problems. And that's what we do to classify the relationships. To explain, let's start with single operation relationships. The simplest kind of relationship that we see is called direct superposition. This is a kind of a relationship where the value of one of the quantities, Q2, is equal to a constant, so a known value, a known number, and then we have the key part, which is plus Q1. You add Q1. Note that Q2 is isolated. Now K is called the constant. And in this context, constant means that it has a known value for a given problem. For some problem, its value may be 4.5. In a different problem, its value may be 3.8. But once it picks a value, that value will not change. The next simplest kind of relationship that we see is called inverse superposition. And these are the kinds of equations where Q2 is equal to a constant minus Q1. The third most complex kind of relationship that we see, or my apologies, I guess the third simplest kind of relationship that we see is direct proportion. And here Q2 is equal to K times Q1. You notice how we are going ahead with increasing level of difficulty of the kinds of problems that we solve. Direct superposition deals with addition of Q1. Addition is the simplest kind of operation that we do. Next, we have inverse superposition, and that has to do with subtracting Q1. Subtraction is the next simplest kind of operation that we see. And then we have multiplication, and I guess you guessed it, inverse proportion. Now we divide by Q1. Now we can go on and talk about more of these kinds of relationships. Usually, the next relationship that's discussed is the power relation, where Q1 goes to a known exponent. We have the inverse of power relation, which is the root relation, and that's taking the kth root of Q1. Next, we have exponentials. A constant goes to the power of Q1. Differentiate between a power relation, where the constant is the exponent, and the exponential relation, where the constant is the base. These are different kinds of problems. And the inverse to exponentials is logarithms. And here we get log to the base k of Q1. You do notice that these are inverse operations. Direct superposition, inverse superposition deal with addition and subtraction. Direct proportion, inverse proportion. Deal with multiplication and division. These are inverse operations. Power relation. Going to a known exponent. The inverse is the root relation, taking the kth root. Exponentials, constant to a variable. Logarithms, log to the base k of the variable. And we can go on and talk about more of these single operation relationships. Now, if these were the only kinds of relationships that we had, then math would be much easier than it is now. The fact that we have so many different kinds of relationships comes from the fact that we can combine these simple relationships into more complex ones. You do notice that in these relationships there is only one operation that applies to Q1. That's why we call them single operation relationships. Here Q1 is being added, Q1 is being subtracted, multiplied by, divided by, and so on. Now, we can combine these basic relationships in different ways. So as an example of that, if we take direct superposition, inverse superposition, direct proportion, and the power relation. So if we allow addition by Q1, subtraction of Q1, multiplication by Q1, and Q1 to the power of a constant, then we call these relationships polynomials. An example is Q2 is equal to 3Q1 to the power of 2 minus 2Q1 plus 4. You notice that Q1 is being multiplied by here. The term that Q1 is part of is being subtracted. In term number 1, Q1 is going to the power of 2. If we allow the first 5 relations, so addition by Q1, subtraction of Q1, multiplication by Q1, division by Q1, and Q1 to a known exponent, we refer to these as rational functions. An example, Q2 is equal to negative 2Q1 squared minus 3 divided by 4Q to the power of 3 plus Q to the power of 2 minus Q plus 1. So basically a polynomial divided by a polynomial. And of all the different kinds of combinations that we can come up with, one is very special. This one takes the first 3 and combines them. Such combinations are referred to as linear equations. An example is Q2 is equal to B plus M times Q1. B and M are constants. So you could have Q2 is equal to 3 plus 2.8 times Q1. These are known as multiple operations relations because of the fact that Q1 is being subjected to multiple operations, now either directly or indirectly. As an example of that, Q1 is being multiplied by here, and the term that Q1 is part of is being added. So linear relationships have equations that are the same as Q2 is equal to B plus M Q1, with B and M being constants. Any equation that has any of the other elements, such as division by Q1, Q1 to the power of a known exponent, kth root of Q1, and so on, is nonlinear. Now, in the next few videos, I will be taking up the topics of direct superposition, inverse superposition, direct proportion, and inverse proportion, and look at each of these individually. Following that, we will take a look at linear equations, which combine the first 3. And after that, we'll take a look at some of the other relationships. Thank you very much for watching.